Hi, everyone. It's John Frensley with World's Finest Physics again. And this time I'm going to talk to you a little bit about how I teach taking integrals in order to find electric or magnetic fields. This is a Physics C, electricity and magnetism, calculus based electricity and magnetism topic. So this is in the middle of my notes here. I'm just kind of showing you what comes before this. So I'm not going to work the whole thing out. I'm just going to show you that I'm going to talk to students about finding the electric field from two charges with this x-axis symmetry, and then two opposite charges, right? Right. Nothing really, special there. And then what I'm going to do is we're going to move on to continuous charge distributions. The first continuous charge distribution I do looks like this. It's a ring of charge. So we find out that you get the same electric field if you model it as two half Q and another half Q that creates electric field that way and creates electric field that way, and then you just take the components and off the race you go. And I make them like graph the electric field shape as a function of x distance and that kind of thing. Okay, so that's easy. That doesn't require an integral. And then I say, okay, well, in general, you have to take the charge distribution, break it up into little pieces, find the tiny electric field. The tiny electric field is k tiny charge over distance squared for that one piece. And then to get the total electric field, you have to take each of the little k dq over r squared. You got to add it all up, right? So we're having that conceptual discussion there. Then the first one I do is an arc of charge. First, I have the students analyze this sort of discrete situation right here, right? Write an expression of the electric field. So they'll be like, okay, electric field there, and then an electric field there, and then an electric field there, right? And then they're going to, kq over r squared plus kq over r squared plus kq over, but they have to do a couple of, um, cosine 30 degrees, right? And then they're going to do it again for B. And then they're going to do something kind of, what could you do in order to reduce the ink or pencil lead you use? And what do I want them to do is I want them to do summation, right? Sorry, my lights in my classroom want to go off on me while I'm in the middle of recording. So, okay. So I'm going to have them do like a summation, right? They're going to find out that the K and the Q and the R squared comes out, but the sum and the cosines of the different things, right? Each of these are going to have a different amount of cosine, right? Are going to cancel out, right? And then I do, this is inspired by a ranking task from the Tipper's book on E&M. Rank these if they have the same charge per length density, and then if they have the same total charge of the rod, right? And so now I've done all that conceptual stuff, and now it's time to actually integrate to get the electric field, at this point at the origin due to this arc of charge, total charge Q, and it goes from negative theta to positive theta, right? So I have these kind of lead-in questions, and then this is my flowchart organizer, right? This is what you came to watch this video for, is so you can see this flowchart organizer, right? So when students have to set up the integral, that's setting up the integral to find the electric field. The setup of the integral is what's difficult for them. They don't know what to do. So the flowchart kind of helps them think their way through it. So first we have to choose a variable of integration. It should be a length or an angle. It should point to different pieces of the charged object. So here, what are we going to do? We're going to break this into a bunch of little tiny pieces, right? Each little piece, like maybe this piece right there, or that piece right there, creates a tiny electric field at the origin, right? So my integration variable needs to be a different number for each piece, a different real number for each piece, right? So I think I'm going to choose my integration variable. My integration variable is going to be phi, because there it is. Phi equals negative theta. Phi equals pi. I'm not going to use theta because theta is already a feature of the physical arc that might exist in real life. Phi only exists in my mind. So, which represents, I want my students to say what that represents. The angle piece makes with the x-axis, right? And I want them to say the limits, that phi is going to go from lower bound to upper bound. Well, this phi, the first piece is negative theta. The last piece is positive theta. So from negative theta to positive theta, I want them to write anything that's a constant. That means as I go from piece to piece, what stays the same? Capital Q is the same. That's a constant. So is R. So capital Q and R. And if you want to throw an integration constant, the Coulomb's law constant K, theta is also a constant too, because these three things all describe the arc itself. The phi is just what I'm using to make an integral, right? Okay, first decision. One of the things you find out about these charts, Easy decisions go left, hard decisions go right. So if you go right, that makes it a little bit more difficult. But if you go left, it's easy. The charge density is uniform because it says total uniformly distributed over its length. So we're going to shade in that this is a uniform charge. This is the path we take. All right, that's the decision we made. All right, so when you have a uniform charge density or uniform any density, you can set up a ratio. The ratio is going to be, look, tiny charge. I put in the DQ for them. Here it says tiny integration variable. Why? Because the integration variable could be a length. If the integration variable is length, this would be a tiny length. If it's an angle, this would be a tiny angle. So because the integration variable is a phi, which is an angle, then this is dq d phi, the tiny piece of charge in a tiny phi. I even did that for the students right here, where this piece is a little dq, a little d phi. So a little d phi angle, tiny angle, cuts out a tiny dq piece. All right, so set up a ratio between dq and the variable d phi, solve for dq. Well, I haven't finished my ratio yet because if you have a ratio, then the ratio is tiny over tiny equals whole over whole. What's the whole charge? The whole charge is capital Q. That's the whole charge. What's the whole angle? Remember, this is an angle that we're talking about. So the whole angle of the whole arc is going to be 2 thetas. That theta and this theta, 2 thetas. So that's 2 thetas. So dq over d phi is q over 2 theta. Tiny charge over tiny angle. I was about to say tiny length. Whole charge over whole angle, right? So that means dq is going to be, dq is going to be q times, q over 2 theta times d phi. All right, it's just solving that ratio for dq. Just multiply up, then you're done. Okay, so we're going to recombine with the other route that we didn't take. Next page. All right. Each of these decisions, by the way, is its own image file. So this is actually a separate picture image in the Word document from this and from this. That way, when these bleed over onto another page, it's easy for you to choose where is the flow chart going to, get chopped up by the page break, right? All right. The distance from each piece to the point of interest P. All right, this is the point of interest right here. That's this green dot. That's where I want to know the electric field. Not here, not here, not here. I don't want to know the electric field here. Don't want to know the electric field here. Don't want to know the electric field here. I want to know the electric field here at the point of interest. Each of these pieces is the same distance from that point of interest. So I'm going to say the distance from each piece, point of interest P, is the same. Okay, we get another left turn here. Yay. All right. Write an expression for the distance r that all pieces have. Oh, well, that's just the big R. Isn't that the big R? That's the big R. It's right there. Okay. All right. So we're going to come back together. Yay. Okay. Do you have to deal with components? The answer today is yes, which is difficult. So we're going to be taking a right turn now. Yes, we have to deal with components. Why? Because each of these pieces creates electric field that points in a different direction. So I have to only take the X components. So what am I going to do? I need a trig function of some kind of an angle. So the angle is going to be phi. Here's the angle phi. That is also the same angle phi. So cosine phi. I need to turn cosine phi into an expression that has constants in it and the integration variable. Well, it turns out the integration variable is still phi. That's the integration variable, right? So cosine phi is just cosine phi. The component maker is going to be cosine. Now, I know you're thinking, wow, what a waste of time. But just wait until we get to another situation where cosine phi or theta needs to be expressed in terms of x or y because our integration variable is x or y. You're going to see it in a moment here. Okay, so we're going to build our integral now. So we just did each of the pieces of the integral. So what am I going to do? I am going to take, let's look. Okay, in blue, we're going to go from negative theta to positive theta. So I'm going to say from phi equals negative theta to phi equals positive theta. I know that people don't do this with limits mostly. They usually go from like negative theta, positive theta, or 2 to 4 or whatever. But I put the integration variable equals like t equals 0 to t equals 1 or x equals 0 to x equals 1. Because in physics, the integration variable could be a t or an x or a y or a theta or a phi, right? So I put the integration variable there. I know they don't do it in calculus because it's always x, but right now it's going to be phi. Okay, what was my expression for dq? dq, here we go. 2 over q over 2 theta d phi. Q over 2 theta d phi. You see, expression, I'm just building the integral, just building it based on what we said. Okay, what's the R? The R is big R. So the expression for there it is. So just each piece is just getting plugged in. Each piece getting plugged in. And then the component maker is cosine phi. So now what am I going to do? I'm going to dress this up. Let's take out some constants. How about K, Q, 2, theta, R squared, and I just get cosine. Oops, that was supposed to be a d phi, not a d theta, d phi. All right, so you just get cosine phi, d phi. We're going to go from phi equals negative theta to phi equals positive theta, right? And then this is just a joke, right? That's a pathetic joke that you just get KQ over, I think it just winds up being KQ over R squared theta times sine of theta, something like that, right? You figure out the integral. The point of the flow chart is to help the students set up the integral. Okay, so now time for line of charge. So once again, I'm going to do this like discrete first, where the students have to say, okay, there's a KQ over this, a KQ plus a KQ over this squared plus KQ over this squared plus KQ over this squared, right? And I'm going to make them, format your answer so you use the least amount of ink. So am I looking for them? I'm looking for a summation with K and Q out, but something squared has to be inside, right? Something squared's got to be inside. Then they're going to do it again for what if the charge was bx squared? So this would be a Q of 0. B d squared, b times 2d squared, so 4bd squared, 9bd squared. They're going to do the same thing, right? That's like a variable density. So you see what I'm doing is before I make the students analyze the continuous, I make them do a discrete as well. I also do this when they have to do center mass integrals and rotational inertia integrals in the mechanics side. They're going to do it with dots and set up a summation before they do the integral. Then I'm going to have them do another piece like this, just a ranking task, right? Okay. And then it's time to actually do the charge on a rod, right? So here we go. Write an expression of total charge of the rod, whatever this is, lambda L or something like that, right? It's a Q equals. Okay. So what's my integration variable going to be this time? Probably X would be a good idea. And it looks like X is going to go from 0 to L. So I'm going to say this is a position of a piece on the x-axis. Okay, so the K and the L and the A. A is the location of the point of interest, right? So that's a constant. That's not changing in the middle of the story. And the lambda is too. All right, the charge density is uniform. So we're going to come over here and say it's a uniform charge. This is the part that's kind of tricky for students. Is it the uniform charge density dq over dx? Because that's the integration variable. X is the integration variable, right? Okay, so it has to be dq dx. Well, this whole charge over whole x, well, you could say it's lambda L over L, right? Because that's the whole charge is lambda L over the total length is L, or it's just lambda, right? So if you're given a density like lambda, a constant density, then you just put the lambda or the sigma if it's an area density, or the rho if it's a volume density, you just put it right here, right? So anyway, so that means dq is lambda dx, right? So you didn't need this side to be a fraction. I don't know a better way to do it than that. So I just tell them that's lambda right there. Okay, yay. Okay, this is different now. This is not the same as it was before. Before, we had an R that was different, that was the same. We had an R that was the same for every piece. Here, the R is the same for every piece. Here, the R is different for every piece, right? So I need to come up with an expression for R. Oh, and by the way, I don't know if you noticed, but the whole R business is before this page break, but this R business was after the page break because each piece is its own image file, right? That's why I did it that way. All right, so each different distance is different. So I need to have one piece that is at location X. Okay, so here it is. That's one piece that's at location. That's X right there. I need to know what this is. This is R. That's the distance from that piece to the point of interest. So what is this R? Well, R and X together make A. So if A is X plus R, then X should be A minus R. So I'm going to say this is A minus R. Okay, good. We did our job there. Do I have to deal with components? No, I don't have to deal with components. Yeah, that's my favorite direction to go is left. So I love going left. I don't have to deal with components because every single one of these pieces is going to make right electric field. So there's no reason to deal with components. All right, so thank you for nothing. Okay, so now I got to build my integral. Let's come back here. We're going to go from x equals 0 to x equals L. So x equals 0, x equals L, right? Okay. What's my dq? My dq is just lambda dx. Lambda dx, right? This is just a scaffolding, okay? All this is scaffolding, right? Your students have to be able to do this kind of crap on their own. They're not going to get this structure on the AP exam, but gosh, it makes it a lot easier on you if you just give them like a decent scaffolding first, right? Okay, there's no need for a component maker, so I'm going to say k lambda, and then this becomes dx. Oops, I meant to say a minus x, and there goes the light switch again, right? Okay, school really wants to save money on these super efficient LED lights that probably cost 10 cents to run for 8 years. Okay, so that was a minus x. I meant to say, did I say a minus x over here? No, I meant to say a minus x over here. You see, I'm going so fast, not even paying any attention, right? So this is supposed to be a minus x, and I could restart the video, but I'm not gonna. So this was supposed to be a minus x. Yeah, this is supposed to be r was a minus x. That's what it's supposed to be. So a is x plus r. So r is a minus x. Remember, everything has to be in terms of the integration variable. That's the theme of the whole flow chart. In terms of x, in terms of x, in terms of x. This would have to be in terms of x, but we didn't need any components. So this is actually supposed to be a minus x squared. Right, x equals 0 to x equals L, right? And so you evaluate and you get whatever it is. Okay, then I'm going to make the students do a non-uniform line of charge. So notice that here is the density function. That's the density function right there. And we're going to go from x equals L to the other end can be treated as infinitely far away. Okay, first state the units of A. It's just a warm-up question, right? Okay, derive an expression for the total charge on the rod in terms of A and L. I don't have a flow chart for this, but students need to know that, you know, charge is integral lambda dx, right? Because what is lambda? Lambda is decharge dx, right? And so let's see, decharge equals lambda dx. So if you want to undo a d, you got to turn it into an integral. So I need to take the integral from x equals L to x equals infinity. Then I'm walking them through this. Is probably the first time they've done this with charge, at least. They've done it with mass and center mass, that kind of crap before. So you get whatever you get, right? I think it just winds up A over L or something like that, right? That winds up being the Q. Let's see what the units of A are. I really should. So that is coulombs per meter equals A over meters squared. Okay, so put little unit brackets on it. So then A would be in units of coulombs times meters. So A is in units of coulombs times meters. So that would be coulombs times meters over meters. That is coulombs. Okay, I just want to make sure that I'm not making an ass out of myself, which is probably going to do a lot because I go too fast. I'm just trying to get this video over so I can go home and have a hamburger. All right, so my integration variables again are going to be x, the x position of each piece, right? The variable is going to range from x equals L. That's the first piece to x equals infinity. I'm not going to do that's way over here. It says it can be treated as infinitely far away, right? All right. So here, the only constants are A and L and the Coulomb's law constant K if you want it to be. Not even the density is uniform. So notice I now have to turn right. I have a non-uniform charge density, right? Well, I need to express dq in terms of dx. Remember, x is my variable. So it says d variable, dx, right? So what is dq? Well, if dq dx is lambda, which is a over x squared, I think that's what it said right there. Okay, then dq is going to be a over x squared dx. I just multiply the x squared. Oh, well, there's the dx right there. Whatever, you get the idea. So it even says what to do. Just put your density function right there. Okay, so the distance to each piece is going to be different. Let's not screw this up this time. The distance from the point of interest to each piece looks like it's just good old x. Well, that was easy. All right, so just it's x this time, so I didn't have to think too hard about that. Yeah, okay. All right, do I have to deal with components? No, that makes me happy. I hate dealing with components. Screw you. Okay, so what have I got now? I have to do, I'm building my integral. So you see how the whole flow chart works. You're building the integral. You're building the x equals L to x equals infinity. Okay, next piece is the density. That's the expression for dq. The expression for dq, that came from right here. A over x squared dx. Okay, no need for a component maker. and the r itself is just x. So then if I wanted to, I could factor out a k and an a. K and an A. I'm going to go from x equals L to x equals infinity. And I'm going to have a 1 over x to the fourth dx. And you do that on your own time. All right. This probably has L cubed when you're done with it. All right. So the last one I'm going to do, and if you're talking about AP Physics C, it's not really important that students evaluate this integral. It's really more important that students be able to set up this integral. And that's the vertical line of charge. So again, I'm going to make the students do this in discrete, which means they have to say, well, gosh, just for this blue one, it's going to be k q over r squared times some kind of a component maker, right? So it's going to be k q over, okay, it looks like 2d squared. That's the and then b squared, right? All right. So that's the hypotenuse. R squared is 2d squared plus b squared, right? You seeing this? Okay, and then we need a component maker. So the component maker needs to do adjacent, that's b over hypotenuse. So that's another square root of a 2d squared plus b squared. And then I'm going to want them to do this in as short a form as possible. So really I want them to have like a sum. So it might look like this, KQB over maybe ND squared plus B squared to the 3/2, where N goes from -2 to +2 or something like that, right? Does that make sense? Like that's what I mean when I'm trying to get them to write a sum, because now they can see that this is going to come out and they've got to deal with a different R distance and a component maker. Okay, so now here it comes. This is a big crescendo. I am absolutely not going to evaluate this integral for you. So if you're hoping, then go to Symbol Lab or something like that. Get them to integrate for you, right? Okay, so this is a vertical line of charge. It's all positive. I'm going to use y as my integration variable. It's the y value of each piece. All right, it's going to go from -a to +a. You see it right there in the diagram, right there. Okay. So what constants do we have? A, B, lambda. All right, so A, B, lambda, Coulomb's law constant K if you really care. And that looks good to me. The charge density is most certainly uniform. The actual charge per length is lambda. I just gave you that, so you don't need this side. You just need dq dy. Tiny charge over tiny length. The whole charge over the whole length is what lambda is. So dq is lambda dy. The variable is y. Okay, I got to turn left that time. That makes me happy. But now I have to turn right, and I have to turn right one more time, and those right turns are not fun. The distance from each piece, u, to the point of interest P is different. So I need to have an R in terms of Y and constants. In terms of Y and constants. So let's say that this piece right here is the piece that is at height Y. This is Y, this is B. This distance right here is the R. Okay, so that's going to be R squared. Let's make sure I do this right this time. Equals Y squared plus B squared. So that means that R is the square root of Y squared plus B squared, or you could say it's Y squared plus B squared to the 1/2 power. Okay, yay. Okay, that's, again, to what extent are you expecting your students to do this by themselves? I do a ton of think, pair, share during this. Each of these steps is a think, pair, share time. I play music, and then we talk, and then we do the next piece, right? And the students eventually kind of get into it, right? But there's no way I'm sending them off on their own to do this without doing all of this first. And maybe the first one I'm going to model on my own. But then as we go, it's a lot of think, pair, shares and a lot of guidance, right? Being guided, all right? Yes, I have to deal with components, you jerk. Okay, so this is, you just did, what did you do last time you had to deal with components, friends? Like, you just said cosine phi equals cosine phi, right? What a freaking waste of your time, right? Let's go back and revisit. Yeah, cosine phi equals cosine phi. Well, see, now it's going to be different. Watch. If this is theta, then my component maker, that's also theta. That's alternate interior bullcrap. Whatever that theorem's called. I need cosine. Cosine. And I need cosine of theta, but theta is not my integration variable. Theta is a variable because the theta is different for each piece. But that's not the integration variable I chose. Now, is it? I chose y. So I need to put something here that's in terms of y. What is cosine theta? Cosine theta is adjacent b over hypotenuse, which you can call r if you want, or you can call it y squared plus b squared to the 1/2 power. So notice, while cosine theta, I could have just used cosine theta before because theta was the integration variable. You remember? Okay, you remember here? Oh, it was phi. Phi was the integration variable here. So I could just say cosine phi is cosine phi because it's already in the terms of the integration variable. Yay! Here, cosine theta is not the integration variable. The y is. So that's why I got to do that. That's why I have to deal with y. Okay, so anyway, so we're going to keep going here. All right, I'm going to build my integral. Let's have a look at this. Y goes from negative a to positive a. Y goes from negative a to positive a. Okay, and then I've got to deal with this, lambda dy, lambda dy. Okay, and then I've got to do with the r. So the r is going to be y squared plus b squared to the 1/2 power. That's going to get squared. And then I have to put in my component maker. B over y squared plus b squared to the 1/2 power. Okay, let's simplify this bad guy. K and lambda are constants. Oh, so is b, because b can come out. Did I put those in my constant list? I mean, if I forgot a constant, I'm not going to bite a kid's head off, but it sure helps if they can remember what their constants are at the beginning, right? Okay, so k lambda b. So I'm going to have a dy. I'm going to go from y equals negative a to positive a. Okay, so what am I going to do here? This is a full exponent here. A half to a squared is a full exponent plus another half. So that's y squared plus b squared to the 3/2 power. Okay, now this is an integral that your students will never have to take on an AP Physics C exam. They may be asked to write the integral, or they might be asked to choose the correct integral in a multiple choice, but not be asked to evaluate this integral because this integral requires trigonometric substitution, which I don't even think the calculus BC people do trigonometric substitution. So the website you can go to, Symbol Lab is one word, and I would look up definite integral calculator, and that'll calculate it for you. I just make my students do that. And then we find out that if B is way bigger than A, so in other words, if you're way the frick far away from the line, then the expression starts to look like KQ over R squared. So let me just tell you that if you're really far away from, sorry about this, if you're really far away from the finite uniform density, finite length line of charge, or if you're very far away from the ring of charge, then your expressions start to look like KQQ over R squared in the limit where R gets big. I don't do this for the arc of charge because the arc of charge, you can only find the electric field specifically at the origin. There's no other point in the XY plane where we know the electric field value the way we do with the other distributions where we know the electric field at every single value of X, for example. That's an infinite number of possible points. And then we find out that if you get super close to the line, then it looks like this. It looks like electric field equals 2K lambda over like R, where R is the distance from the center of the line. And they're like, okay, whoop-de-frickin' do. But then after we do a long line of charge using Gauss's law, we actually come back and see this again and find out, yeah, well, you could have used Gauss's law. If you assume that the line is super long and not finitely length, then you could have used that much easier, right? Okay, so that's my nifty flow charts for continuous charges. I like them. You know, it's a scaffold, right? All right, next video, I'm going to talk about Gauss's law flow charts and kind of a little bit of how I teach Gauss's law.